Смотрите.
Вот картинка есть, мы видим все.
Хорошо. Let's start. Hello, dear my friends. My name is Liang Qing. I'm a PhD student in the Department of Information Navigation System. Today, very pleasure to give you a lecture about the random sequence. In the past lecture, all the algorithm and methods for their solution is about the estimation of vector, which is unchanged in time. More general is the situation in which the parameters we need to estimate is changed with time. So such tasks that we'll discuss in this and next lecture. First of all, we will give the description and properties about the discrete sequence. Then the professor will give you a lecture about the Kalman filter, which is the most important part of our course. Let's go start. Our lecture consists of the following section: definition of a random sequence and its description, stationary random sequence, discrete Markov process, and shaping filter. And in the last, we will talk about the dynamics of the covariance matrix for the Markov sequence. In the first section, we will give the definition of a random sequence and discuss the method for describing it. Consider a sequence of scalar variables x1, x2, x3, xi. Here the index 1, 2, 3 is corresponding to time. Here is the picture showing the many samples of a random sequence. A sequence is called random if each random variable is random. In the estimation theory, if we want to describe a random variable, we use the probability density function to describe it. So we can also use the probability density function to describe the random sequence. A random sequence can be fully described by using the joint probability density function at an arbitrary time point. If you get the joint probability function, density function, you can get many important information from here. For example, these three important functions. First of all, the mathematical expectation, just like here, and the variance by this equation. One of the most important for description of a random sequence is the autocorrelation function of a random sequence, which is used to describe the relationship between variables at different time points. This function is the most important for us. It gives us many information. In particular, if I equal to j for correlation function, what we will get? I think you all know we will get if I equal to j, the correlation function coincides with the variance. This three function is most important. It can help you to understand a random sequence. Of course, there is other function, for example, mean square value. Let's say some effect of parameters changing on a random sequence. If we change the mean, we get the three random sequences with different means. If we change the variance, we get also the different random sequence with the different variance. Of course, the random sequence may be not only scalar but a vector as well. The term random n-dimensional vector sequence is used in reference to a sequence whose variables are n-dimensional random vector. Assume that we have a random vector sequence x1, 2, 3, i, where xi is an n-dimensional random vector at time I. We also can use the joint probability density function to describe a random vector, just like we want to describe a random scalar sequence. At the same time, we also can get the mean or random vector, just like here. Variance for a random vector will, in this case, will be changed to the has another name, which is called covariance matrix, which is equal to correlation plus the variance. Variance in correlation matrix is on this line. Other elements are correlation values. This matrix shown as the correlation matrix for random vector sequence. Also, we can get the correlation function that's shown in this matrix. There is some important properties for you. I think you all know about it. Let's remember it. If a random vector plus a constant matrix, it changes the mathematical expectation. The variance for vector will shown in by this equation. The correlation for two random vector will shown in by this equation. Here is interesting. If we want to get the variance of two random vector, if they are uncorrelated, the variance will be equal to the sum of each variance of random variables. I think you need to remember this. Here is one question for you. If z equals ax plus y, A is constant matrix, and x and y are uncorrelated, what will be equal to the variance z? You have 1 minute to do this task. Have you understand this question? Yes, okay. I wait. You have 1 minute. Have you gotten the answer?
We're still calculating.
Okay.
So we got the answer.
Mm-hmm.
It's A times variance of x plus variance of y.
Okay. Let's check the answer. Here's the answer. Because x and y are uncorrelated, so here variance will equal to the sum of each variance. So it will be equal to here. Are you right?
Yep. Yes.
Okay, very good. This conclusion is very important. We will use it in the following part of this lecture. So I think you are we need to remember it. The next, after the definition, I will introduce you some common random process. First of all is the stationary random sequence. Stationary random sequence is one of the most important class of random sequence. His typical example is the stationary white noise. Stationary random sequence has two definitions. Stationary random sequence in white sense and the strictly stationary sequence. In the white sense, stationary random sequence is a sequence whose expectation doesn't not depend on the time and the correlation function depend only on the difference. So his expectation didn't change with time, and his correlation function is just depend on the difference. From the correlation function, we can get the variance of the stationary sequence didn't depend on the time, so it also didn't change. For strictly stationary sequence, his definition is that his probability density function introduced for any finite set of variables or sequence remains unchanged when all time points changed at the same time by a value mu. So his probability density function will remain unchanged when we change the index, when we change the time at the same time. These two definitions we all can use to say the random sequence is stationary or non-stationary. From the strictly definition, we can get if their probability density function unchanged with time, their expectation and the correlation function is will have this form. If the above the list properties are not met, this sequence is called a non-stationary one. There is another concept which is called zero mean sequence or non-zero mean sequence. Zero mean sequence is a sequence whose mathematical expectation is unchanged with time is equal to 0. This picture shows the zero mean sequence, and this shows the sample of non-zero mean sequence. We need to know that. Zero mean sequence has maybe zero mean non-stationary sequence, zero mean stationary sequence. For example, for here picture shown one sample non-zero mean stationary sequence whose mathematical expectation is equal to 1. He is a stationary sequence, but it's not non-zero mean sequence. Zero mean sequence may be non-stationary. For example, here, if their mathematical for initial time points, their mathematical expectation equal to 0, this random variable will remains unchanged by mathematical expectation, but their variance will be increased, just like here. So zero mean may be non-stationary sequence. So only one function we need to check is that this function is mathematical expectation is equal to 0 or not. In practical, we often deal with one typical random sequence which is called white noise. Well, white noise is a sequence that the variable which are uncorrelated with each other at different time points. So their correlation function will have this following form. his correlation function just depends on this time, and this delta here is a Kronecker symbol. From here we can say the white noise may be non-stationary because their variance may be changed with time. So if the white noise is zero mean and the variance for all time are the same, the white noise will be stationary. For the white noise, we can easily get his distribution function. Before this, we need to repeat some concept, dependence and correlation. I think you didn't forget it. From Bayes' rule, we can know this equation. If the random variable xi and xg are not dependent, we have the joint distribution function will be the product form of each distribution function. Easily to know if there are two independent random variables, they are also not correlated. And if there are two random not correlated variables, it doesn't necessarily mean that they are independent. But if the random is Gauss variables are not correlated, they are independent. So if the white noise with the Gauss density function, his probability density function will be the product form of each probability density function. It's just like here for Gauss white noise. Let's introduce another another useful random sequence, which is called Markov process, named by a famous scientist Andrei Markov. Andrei Markov was a Russian scientist. He is best known for his work on random theory. He had studied in St. Petersburg University and died in July 1922 in St. Petersburg. Primary subject of his research is later became known as Markov chain and Markov process. His son, another Andrei Markov, was also a famous scientist in Russia. We often use, as we cited in the first part of the lecture, we use the joint probability density function to describe a random sequence. By using the Bayes law, we can write it in this form. It consists of two parts. One part is the initial probability density function for initial variable. Another part is the conditional probability density, which means the variable at current time depend on the previous time, depend on all previous time points. This function may be used for describing all the random sequence. In particular, if the probability density function, the variable at current time depends only on the previous time and not depend on the values of the sequence at time point t less than the tk minus 1, we get this sequence will be called Markov sequence. And at the same time, this conditional probability density function is called transition probability density function. So this is the most important characteristics for Markov sequence. His transition probability density function just depend current random variable at current time just depend on the previous random. So for Markov sequence, the joint probability function can be written in this form. It consists of two parts: the probability at the initial time and the transition the transition probability density function. So specification of the transition probability density function and the probability density function for the initial time are sufficient to find the joint probability density function for a set of Markov sequence variable at any time point. This feature gives us great convenience. It made us to use the Markov process to model a many important random system, including the communication system, transportation networks, image segmentation and analysis, population studies, financial engineering, and of course our navigation system. For example, we often use the differential equation to model an object. The mathematical model stability by the differential equation is easy to satisfy the definition of a Markov sequence. And the state space model, I think you all know, which is often used in control system theory, is also easy to be applied to describe Markov sequence. So we need to know how to use Markov sequence to describe the random sequence. Let's go to the next part. We use the shipping filter. In practical, shipping filter plays an important role to describe the random sequence. Here we use this function. This function is the most important function for shipping filter, where xi is an n-dimensional vector, and the initial vector is uncorrelated with the input noise, which is wi, which is a zero mean p-dimensional discrete white noise with the correlation function described as following. It's just a common white noise. From this equation, we know that the variable at current time just depends on the variable at the previous time. So this equation describes a discrete Markov process. The shipping filter gets its name because the input white noise can be shipped by shipping filter into the random sequence that you want. Of course, if we know that if the variable of the sequence at the initial time and the variable of the white noise are Gauss, just like here, their probability density function will be written in this form, this sequence will be called a Gauss-Markov sequence. And from this equation, we can get their time evolution of expectation and covariance matrix. Just use the conclusion of the x-axis. So just like here, xi is equal to this matrix on mathematical expectation and previous time, and their variance will equal to here. Just the matrix. I think you know that because this conclusion you have did it in the exercise. In the common filter, this two equation has another name, prediction. You will know that in the next lecture. Let's introduce two important random sequences by using the shipping filter. The first is called Wiener process. Maybe has another name called random walk. His shipping filter is written in this form: xi equals xi minus 1 plus the wi. In this case, Wiener's process, we often think that the initial mathematical expectation is equal to 0, and the white noise is his expectation also 0. It's not difficult to get their mathematical expectation because at each time their at each time, the mathematical expectation for each random variable will equal to 0. It's not difficult from here to get this function. And for variance will be in this form. There is a little error. There is not I. It just current variance at current time just equal to variance at previous time plus this one. There is not I. So we can easily get the variance at current time will equal to the variance at initial time plus this I multiply on the Q square. You will know the variance for the winner process will increase with time. It will increase on time. So the winner process is of course not a stationary random sequence. We often not difficult to get the correlation function. It's just like here. It's equal to the minimum variable variance at time g and time I and time g. The winner process is often used to describe the integration error for the MEMS for in or navigation system for the MEMS. There is another important random sequence which is called first order Markov process. His shipping filter is represented by this equation. Here, also the initial mathematical expectation for the initial time is also equal to 0, and the input white noise, his mean also is equal to 0. Also, we can get the mathematical expectation for the first order Markov process is always 0. The variance in this time will be in this form. It will be in this form. From this equation, we can know that when the time tends to infinite, the variance will be equal to the sigma square, just like here. It means this variance didn't change if we choose the bigger time. We choose the larger time. In this case, correlation function is not difficult to derive. It's difficult to derive. It may be somewhat complicated. We just give the one conclusion. If the initial variance is equal to the variance at infinity time, initial equal to the infinity time, it has a form just depend, the correlation function just depend on the time difference. So easy to know if the initial variance is equal to the variance at infinite time, the first order Markov process will be stationary. We will often use these two processes, Venus process and first order Markov process. So I hope you need to derive all this mathematical expectation and the variance and the correlation function by yourself. From here, we also know that if the initial for the first order Markov process, if the initial variance didn't be equal to the variance at infinite time, the variance will be changed with time. So we need to talk about the dynamic of variance matrix. Let's go to the next part. Dynamics of the covariance matrix for the Markov sequence. Let's consider the following scalar shipping filter. Here xi equal to xi minus 1 plus wi, where in this case for shipping filter, the gamma matrix is equal to 1, and the variance for input noise is equal to q squared. In this case, we can write their time evolution equation for the covariance. It's also not difficult to get this equation. It's over here. We need to discuss if when the matrix phi is lesser than 1, what's the relationship between the variance at the current time and the variance at the past time? It's not difficult to know that if it is minus 1, what's the relation between the variance at current time and the private time? From this equation, we can get that if the time tends to infinity, this we have get the constant variance at infinite time, which is equal to this one. I think you also can get it if the time tends to the infinity, it will equal to the q square on 1 minus phi square. If the initial variance is greater than the variance at infinite time, the variance will decrease with time, just like here. This is just like this picture. So, and at the same time, if the initial variance is less than the variance at infinite time, initial variance is less than the variance at infinite time, the variance will increase. And if the initial variance is equal to the variance at infinite time, the variance metric will remain unchanged, just like here. So there is a steady state variance which is equal to this one, and it's easy to know if the initial mathematical expectation is equal to 0, it will be a stationary sequence for this scalar reciprocal filter. This is dynamics for the scalar reciprocal filter. And of course, we need to talk about when phi equal to 1. When the matrix is equal to 1, this reciprocal filter will be the Wiener process. We have discussed this characteristics. His variance will equal to this one, will be increased with time, and there is a not steady state variance. And of course, if the matrix is bigger, is greater than 1, this his variance will be transformed in this form, and the sequence will be increased with time very quickly. Also, there is a not steady state variance. By using this way, if they'll give you another reciprocal filter, you can also discuss the dynamics of the covariance matrix. What's the next? In the next lecture, we will talk about the Kalman filter using the reciprocal filter. This picture has shown the Kalman has been in St. Petersburg 2 years ago. This is Kalman. This photo was taken when he was with our research group. I think this guy, you know, is Andre. And this guy is Mustafa with me to do this presentation. And no one in this picture is me. In the last, I gave you 2 famous words from Confucius. Maybe it will be helpful for you and convenient for you. Confucius said, "The learning without thought is labor lost. Thought without learning is perilous." I think you understand what this means. And the second word is, if you keep creating your old knowledge so as continually to be acquiring new, you may be a teacher of others. So keep learning and thinking. This is all my lecture. I hope all you get some knowledge that is good for you.
Thank you very much.
Thank you.
Do you have any question?
Sorry. We have a question about the one.
Okay. This one, learning without thought.
Yeah, exactly.
It means if you are learning without thought, you will feel lost. Because you're just learning, you didn't sort what you're learning. You may feel you have learned many knowledge, but you didn't know how to use it when you use it. So you will feel lost. If you the second part, if you sort without learning, you just sort what you learn. You didn't learn new knowledge, so you will feel tired and you can't move forward.
All right.
So it's a very famous.
Thank you very much.
Okay, thank you. There are another. Andre will tell you the result about your home task.
So hello. Here you can see the table of exercises, and plus minus means that there is some conversation about this task, and maybe they're somewhat difficult, and only one exercise is not done, and one exercise I didn't check yet. So it's all, I think, good. So it's the table. If you have questions, please write to your supervisors, or you can ask me as well.
If we have questions about the lecture notes,
About
is there something we can ask?
About the if you have a question about the lecture, you can ask your supervisor, so Ilan Tsin.
All right.
And well, if you have the question about exercises, you also can ask your supervisors or me.
All right.
Okay. If you have no questions, then farewell. Excuse me?
No questions.
No questions. Okay. So that's all for today. Thank you.
Yeah, thank you too. Bye.
Bye.
Keine Aufgaben oder Fragen will ich schicken.
4 минуты, да?
Да. Ну, ты быстро уложился.
На самом деле, я только считаю первый